This is Math 5700. This is lecture number 45. We will begin chapter 8. We're not covering all sections of chapter 8. We're nearing the end of the course. Today we cover 8.2. Okay, so let's get started. Okay, so in what I want to talk about, two inequalities which are useful in getting bounds on probabilities. These are. It's important to note that they're bounds, not approximations. So the first of these is called Markov's inequality. And it goes like this. Suppose, so this is 8.2.1, proposition. So suppose x is, so let x be a random variable. It doesn't matter whether it's continuous or discrete. What's important is that x is never taking negative values. Then for all constants a greater than or equal to 0, we could ask what the area under the distribution for x bigger than a is. So here's our, maybe this is our PDF. We're in the continuous case, so here's a. We're asking for the area bigger than or equal to a of the distribution. And that's bounded above by the expected value of x divided by a. So that's the Markov inequality. This is a bound, an upper bound. You really should not view it as an approximation, because it can be very, very crude, the bound. It may not be very close to the actual probability. But we can actually prove this very easily. So what we're going to do is define a new random variable. Book calls it I, which takes the value 1 when x is bigger than or equal to a, and it's 0 when x is less than a. Okay, so now because of that, we can see that I, this is a function, of course, I is less than or equal to x divided by a, because if x is greater than, in the case where x is bigger than or equal to a, x over a is bigger than 1, and I never takes a value larger than 1. And if x is less than a, I is 0, but x over a is never negative. So this inequality is always holding. Okay, so now then we can now expected values are integrals of non-negative functions in this case, because we're in this case. So the expected value of I is going to be smaller than or equal to the expected value of x over a. But what is the expected value of I? The expected value of I is given by the integral from minus infinity to infinity of I of x times f of x dx, where f is the density function. I'm going to just consider the continuous case for convenience. And now f of x only is defined for x bigger than or equal to a. It's 0 otherwise, so it's the integral from a to infinity of 1 times f of x dx. But that's exactly the same thing as the probability that x is at least a. So the left side of the equation is the probability that x is at least a. And the right side of the inequality, I should have said inequality rather than the equation, is 1 over a times e of x. That's one of the basic properties of the expected value. So this actually shows you we've just checked the Markov inequality. We're done. Okay, so that is that's the Markov inequality. there will be another inequality that I want to establish in a moment called Chebyshev's inequality, but let's do an example. Okay, so let's do an example. Let's assume that the average grade on a Math 5700 exam was 80%. Let's give an upper bound using Markov's inequality on the proportion of students that score at least 90%. That means 90% or more on the exam. Okay, that's scored. Okay, so here's the solution. The point is that let X be let the average grade. So let X be the grade of a student. So then the average grade, that's the expected value, is by assumption 80. So therefore, by Markov's inequality, the probability that X is at least 90, that's exactly what we want to compute. We want to sort of get the upper bound for. That's at most by the Markov inequality, the expected value of X divided by 90, which is 80 over 90, which is 8/9, which is about 0.89. So about 89, so this is the upper bound is that no more than 89% of the students could have scored 90 or more, 90% or more on the exam. Now, this is a very crude bound because it's probably in reality a much smaller percentage of students actually scored 90 or more. Because it is the average grade is 80. It's not likely. I mean, the distribution will look really weird if actually close to 89% of the students scored 90 or more. Again, this is just a bound. It's not to be viewed as an approximation. Okay. So we're still in section 8.2. I want to talk about the so-called Chebyshev inequality. A lot of this probability theory was done by Russians. Markov was a Russian. Chebyshev was a Russian, I believe. Okay, so here is the other proposition of the section or the subsection, proposition 8.2.2. So let X be a random variable, and here we don't need to assume that X is non-negative. So we don't need to assume, no need to assume that X is bigger than or equal to 0. Okay, then for all real numbers, K bigger than 0, we have the probability that, so what I need to know here, I want to set mu equal to the expected value of X, and sigma squared will be the variance of X. So I want to look at x minus mu, and I want to look at its absolute value, and I want to look at the probability that it's at least k. And the statement of the Chebyshev inequality is that that's at most sigma squared divided by k squared. So what I'd like to do is, first of all, illustrate what the left-hand side of the inequality is supposed to be measuring. So suppose the expected value is mu, and the distribution looks something like this, let's say. Okay, so we're looking at here the stuff. So this is the difference between x and mu is going to be this stuff here. Oops, I want to make that a different color. We want to get the area of that kind, and so this is so this distance here should be at least is k. So we want to calculate the yellow area. We want to get a bound for it, that is, and it's saying that there's a bound for that yellow area. It's sigma squared over k squared. So let's give a proof of this inequality. So here's the idea. So here's the proof. Okay, so let's apply Markov's inequality to x minus mu quantity squared. So what does that tell us? Well, x minus mu quantity squared is non-negative. So the probability that x minus mu quantity squared is bigger than or equal to, say, k squared now is at most, by the Markov inequality applied in this situation, the expected value of x minus mu quantity squared over k squared. But now, the numerator on the right side of the inequality is by definition the variance. That's one of the definitions of the variance. So we're going to get sigma squared over k squared. Now, what's the left-hand side? Well, x minus mu squared is at least k squared if and only if we take square root of both sides, the absolute value of x minus mu is at least k. That's absolutely clear. So this is the same thing as the probability that absolute value of x minus mu is at least k. So we get the inequality that we look for. That's the Chebyshev inequality. These are very easy results to prove, notice, using the basic properties of expected value. Okay, so we are done with the proof of the Chebyshev inequality. Let me do an example illustrating the Chebyshev inequality. So let's flip a fair coin 100 times. So let's use the Chebyshev inequality to estimate the probability of having fewer than or equal to 40 or more than 60 or more heads. So that's the probability. I think the word estimate is not good. To bound, I should say. The probability that x is at most 40 or x is at least 60. So here x is the number of heads. Okay. So now when you calculate the number of heads here, it's a fair coin, so p is 0.5. This is X is a binomial random variable with the number of flips being 100, n. So we're doing a repeated flips. That's a number of experiments with p as a half because it's a fair coin, and the number of flips is 100. So X is B and P, where N is 100, B is 0.5. Okay, so that's good to know because then we know what the expected value of X is. That's N times P, which is 100 times 0.5, which is 50. And we also know the variance of X because it's binomial. It's NP times 1 minus P, which is 100 times 0.5 times 0.5, which is given by 25. Okay, so now we can apply the Chebyshev's inequality. Well, so this is sigma squared, and this is mu in that case. So the probability. So notice that X less than or equal to 40 or X bigger than or equal to 60 is the same thing as X minus 50 absolute value being bigger than or equal to 10 in this case, right? Because if that's equivalent, an equivalent condition. So the probability that X minus 50 absolute value is bigger than or equal to 10 is bounded above using the Chebyshev inequality by 25 over 10 squared, sigma squared over k squared, which is given by 0.25. So the answer is the bound is given by 0.25. So the probability that X is less than or equal to 40 or X is bigger than or equal to 60 is at most 1/4. That's what the solution says to this problem. Okay. So usually the Chebyshev bound is better than the Markov bound. So let's do an example which sometimes you can apply both in the same situation. So let's do the case of the following example. You have a biased coin where probability of heads is 0.2, and we flip 20 times. So n equals 20, X equals the number of heads that occur in the 20 flips. So then X is binomial, is B 20, 0.2. Okay, so then let's first of all estimate, not estimate, never use estimate here. Let's bound the probability that X is at most 16. Okay, so now so let's bound. So let's do it in two ways. We have the Markov approach, which says, okay, we have here we know the expected value of X in this case is given by n times p, which is 20 times 0.2, which is 4. Okay, so therefore the probability of X at least 16 is bounded by the expected value of X over 16, which is 4 over 16, which is 1/4, which is 0.25. So that's the Markov approach. But now I want to do the Chebyshev approach. So how are we going to do that in this case? So the claim will be that the Chebyshev approach gives a better bound. So here's the Chebyshev bound in this example. So let's first of all consider the probability that x is at least 16. Okay, so what is that? Well, notice that x being 16, see, x only takes non-negative values. X is always bigger than or equal to 0. So what does it mean for x to be 16? First of all, what is, we know that the expected value of x is 4. We saw that when we were doing the Markov case. So x being at least 16 means that x minus 4 is at least 12. Now, and we also know that so that means x minus 4 is at least 12. But I want to get the absolute value in on this, so let's consider the following. So we have 4, we have 12 over here. There's a distance of 8 between 4 and 12. We also have, I'm sorry, that's not right. I want to use 16 here. So there's a distance of 12 here. Now, what is a distance of 16 from 4 on the other side? That would be minus 8. Distance of 12. So we know that x bigger than or equal to 16 is in this region, is the same as saying x minus 4 is bigger than or equal to 12. But we also know that this is also saying that so x never takes negative values, but certainly x is less than or equal to minus 8. I'm not saying this right. Let me start over here with this explanation. Let me start over. What does it mean for x to be bigger than or equal to 16? Well, we know that that's the same thing as x minus 4 is greater than or equal to 12. But what is the absolute value of x minus 4 equal to greater than or equal to 12 mean? This means one of two things. It means that x minus 4 is at least 12, or 4 minus x is at least 12, which means that x is at least minus 8. X is at most minus 8. Now, this x being less than or equal to minus 8 is an empty condition because we're assuming that x is bigger than 0. So this never happens. What I'm trying to say is that in this case, if we assume x is bigger than or equal to 0, then x bigger than or equal to 16, that inequality occurs if and only if absolute value of x minus 4 is bigger than or equal to 12. Okay, so we put this in an absolute value form, this inequality. That's what we had to do. So therefore, the probability that x is at least 16 is the same thing as the probability that absolute value of x minus 4 is at least 12. And now we can apply the Chebyshev inequality. We have the expected value is 4, and we also need to compute the variance here. The variance here is of x is n times p times 1 minus p, which is given by 20 times 0.2 times 0.8. Okay, so therefore, the Chebyshev inequality says that the probability that absolute value of x minus 4 is greater than or equal to 12 is given by 0.2 times is given by 20 times 0.2 times 0.8 over 12 squared. And you can look this up on your calculator. This is 1/45. This is a much better bound. A much better bound than the bound you got, which was 1/4 using Markov. So let me summarize what I did, because I think it was kind of confusing. So I start off with x being bigger than or equal to 16. And that is the same thing as x minus 4 as being at least 12. But since x is non-negative, putting in the absolute value doesn't change anything. This is an empty condition, 4 minus x being bigger than 12. So having that empty condition there, it doesn't change the inequality. So we replace x minus 4 bigger than or equal to 12 by the absolute value of x minus 4 being greater than or equal to 12. And that enabled us to apply the Chebyshev bound. Okay. So one of the advantages of the Chebyshev inequality is it enables you to give an easy proof of something called the weak law of large numbers. We'll be talking about the law of large numbers next time around. So this is like a preliminary version of that. So here's the idea. So the idea is you start off with x1, x2, an infinite sequence of IID. Remember, that means independent, identically distributed, random variables. For example, think of throwing a die, six-sided die, same die. That would be, there's the first roll, then the second roll, then the third roll. You keep rolling a die an infinite number of times. So rolling the die, E of xi, the expected value, is the same for every die roll. And the variance, let's call the expected value mu, and the variance for all of them will be called sigma squared. And so the statement is then for all real numbers epsilon greater than 0, we can look at the following thing. So we can take the average of the first n of the random variables. Now, the average of the expected value of the average is also mu. We know that. We can subtract off mu. Now we have a new random variable whose average, if we do this subtraction, the new random variable has average 0, and we can look at the probability that is at least epsilon. And let's take the absolute value here. So then, as n goes to infinity, this probability, so if we keep doing more die rolls in this case, as n goes to infinity, this probability tends to 0 as n goes to infinity. The idea being here now that if we do these sample averaging of dice rolls, if you do it infinitely many times, then it's approaching the actual expected value of that average is approaching the actual expected value mu. Okay, so here's the proof. The proof is very simple. We're going to apply the Chebyshev inequality. So let's let Sn be given by this average x1 plus dot 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 plus xn over n, and so we're looking. So then we know that the expected value of Sn is mu, and we even know the variance of Sn. We can compute that because we know how the variance behaves for something of the form ay plus b, right? The variance of ay plus v is a squared the variance of y. So this is of that form, and so you're going to get it's going to be the variance of this is going to be given by so we can compute the variance, and it turns out the variance is sigma squared over n. Okay, so now let's apply the Chebyshev inequality to the situation. So the probability that the absolute value of Sn over n minus mu is greater than or equal to epsilon is at most, this is the bound, the variance of Sn over n. Well, I should have write Sn over n here. It's the variance of Sn over n, which is sigma squared over n divided by epsilon squared. Now, as n goes to infinity, the denominator is fixed. As n goes to infinity, the numerator tends to 0. So this is tending to 0, and that's what we had to show. So we're done. So that's it for section 8.2. We will continue. Next lecture will probably be the last lecture of the course.